Hello, everyone. This is our sixth class, which is statistics and probability, the second part. In this class, we're going to review the distributions that we're going to use during the semester, namely normal, t, chi-square, and f distribution. And we're going to see how we can apply whatever we learned in the previous class, which was the theory of statistics and probability, and what we learned today in R. Okay? So let's begin. Starting from the normal distribution. What is a normal random variable? A normal random variable is a continuous random variable that can take on any values. So remember, this is continuous, it's important, and it can take on any values. Its probability density function, or the PDF, has a familiar bell-shaped curve, which we can see in the curve below. And by the way, guys, these graphs and things that we see in this set of slides is from the appendix B and C from the Wooldridge textbook. So if you're curious to do some more readings, make sure that you read appendix B and C from the textbook, Wooldridge textbook. All right, so the normal distribution, as many of you guys know already, it's a bell curve shape, and it is symmetric. So we talked about it. So skewness is going to be 0. It means that, average, mean, median, and mode are going to completely overlap. So this is one important property of normal distribution. And we say that X has a normal distribution with expected value mu and variance sigma square, and we write it like this. Okay. So whenever you see something, there's this tilde, so we read it, we say X is normally distributed. So the tilde is, we say X is distributed normally with the expected value mu and the variance sigma squared. So this means that if I write expected value X, the answer is mu. If I write the variance of X, the answer is sigma squared. This is how we show the distribution for a normal random variable. And because the normal distribution is symmetric, mean, median, and mode are the same. All right. Let's look at some properties of normal distribution. And because this is one of the distributions that we're going to deal with a lot, and we are going to make assumptions that our variables in the econometric course are going to be normally distributed, and we have to see what are the properties of normal distributions, and basically what are the challenges that we deal with if a random variable is not normally distributed. We have to fix for those things, right? But these are the topics that we're going to cover later on. So what are these properties? We say if X is normally distributed, if I standardize X, remember what was the standardization process? Take your average out, d-mean it divided by standard deviation. So if I standardize X, then that new variable, we can call it anything. We can call it Z, but W, and etc. But let's, for the sake of argument, call it Z, because usually we call it Z score. So this Z is going to be normally distributed with average 0 and standard deviation 1. This is nothing new. We've seen this before already, right? Basically says that if this is your random variable, I have a mu here with the standard deviation of sigma, then the Z transformed version of that is going to be a random variable with the average of 0 and standard deviation 1. All right, second property. We say if X is normally distributed with the expected value mu and variance sigma square, then any linear combination of that, like AX plus B, A and B are constant here, are going to be still normally distributed, but with the expected value of A mu plus B and the variance A square sigma square. So this is where the properties that we covered last class for the expected value and variance is going to come handy. And for instance, if I want to prove, maybe let's prove one of them to you, and then the other one is for your exercise. We can cover it in the class. Oops, let me make sure that. So let me do this one, and this is your exercise. So we want to say that we want to see what is the expected value of AX plus B. I'm using the properties of expected value. Expected value of a constant multiply x is going to be a expected value of x plus expected value of a constant is a constant, right? And we already know that from the previous slide that what is expected value of x? X is normally distributed, so the expected value is going to be mu and b. So this is what we see here. I want you to prove this one. I want you to show me that the variance of a x plus b is going to be equal to a square sigma square. This is your exercise. And then finally, any linear combination of IID normal random variable has a normal distribution as well. So what is IID? It stands for independent and identically distributed. Basically, it says that if you have two independent random variables and they're identically distributed, it means that their distribution is the same. So they're both normally distributed. They both have this different distribution. If you add a bunch of these random variables together, the new output, the new random variable is going to be also normally distributed. Okay, so that's what we're saying in property number 3. And we're going to see this property again when we talk about the distribution of sample averages. So just remember that any linear combination of normal random variables is going to be normally distributed. All right. Now, the rest of the slides is going to cover chi-square distribution, t distribution, and f distribution. So for these one, I don't expect you to memorize anything. No, you're not supposed to know what is chi-square. It's a combination of some standardized normal distributions or random variables. But I want you to realize what are the properties and visually how does it look. So for instance, we start with the chi-square distribution. Chi-square distribution is obtained directly from independent standard normal random variables. So remember, these were standard normal random variables, right? So actually, let me do it this way. So if I take a standard normal random variable and square it, and if I have a bunch of them, and then add them together, the output is going to be distributed with chi-square distribution. And again, for you, the shape is important. And what is the concept of degree of freedom? Just remember, this is your random variable x. This is the probability density function, or we show it with little f, small f. And look at that. The first thing that should pop up in your mind is that this random variable is always positive. So chi-square distribution is always positive. It starts from 0 and onward. So it is important. But normal distribution could be positive and negative, you remember? So maybe it was 0, it can take negative numbers and positive numbers. But chi-square is always positive. And it's not surprising because what? We are squaring the standard normal distributions. So we are squaring all those positive and negative, so the answer is going to be always positive. Chi-squared distribution has n degrees of freedom. So what is degrees of freedom? In general, degrees of freedom is defined as the number of independent observation in the sample. Number of independent observation. We're going to look at some examples later on in the course, but this is the most basic and straightforward definition for degrees of freedom. So here we say the degree of, we show a chi-square distribution. We say x is distributed with chi-square and n degrees of freedom. So this is how you should read it. The degree of freedom in chi-square distribution corresponds to the number of terms in the sum. So how many of these standardized normal random variables we are adding up? That's going to be our degree of freedom. And then finally, chi-square random variable is always non-negative. We talked about it, and it's not symmetric. Obviously, it's not symmetric. So how does it look if we go from degree of freedom 2 and we increase the degree of freedom? So initially it's something like this, and then as you increase the degrees of freedom, it will become some curved shape, but it's not symmetric. So whenever you want to remember what is chi-square, have something like this in mind. Okay, it's going to be skewed, and so it's not symmetric, and it's always positive. Okay, so this is what I want you to remember from chi-square distribution, and know that it's a summation of a bunch of other standardized normal random variables. Okay, the next one is t-distribution. So t-distribution is very, no, at least it looks very the same as normal distribution if you look at these t-distributions. And so the first thing that you see, it's going to be symmetric, like normal distribution. So this means that mean, mode, and median will overlap. It's going to be the same. However, it's going to the curvature is going to be depend on degrees of freedom. So if degrees of freedom is, for instance, if it is 1, it's like this. If it is, let's say, degree of freedom 2 versus degree of freedom 24. As we increase the degrees of freedom, this curve is going to look a lot more like the normal distribution. And in theory, we can see that if degrees of freedom approaches to infinity, t-distribution and normal distribution are exactly the same. All right, how we define the t-distribution? T-distribution is a combination of standardized normal distribution in the numerator and a chi-square divided by its degree of freedom in the denominator. Okay, so again, this is, I don't expect you to memorize, but remember, it's a combination of two distributions: standardized normal random variable and a chi-square random variable. And so for that reason, because we have n degrees of freedom for chi-square, the degree of freedom for the t-distribution is going to be also n. So we say that t is distributed with student t-distribution with n degrees of freedom. Then the t-distribution gets its degree of freedom from the chi-square. Now we talked about it because look at the formula. And then the PDF of the t-distribution has a shape similar to that of the standard normal distribution, except that it is more spread out and therefore has more area in the tail. So we call the t-distribution is fatter than the normal distribution. So let me use another color, try to show you something here. Look at that. Let's say if this df is large enough and it's close to normal distribution, maybe it's close. So if this is my normal distribution, something close to normal distribution, and this is my t-distribution. You see, t-distribution is more fat tail. So the area under the curve for the t-distribution is going to be greater than the area under the curve for the normal distribution. These are important. Later on, when we cover the hypothesis testing, these are going to be important properties. So we should know these things. All right, and finally, the F distribution. Again, F distribution is a combination of two chi-square distribution, one in the numerator and another one in the denominator. So the degree of freedom for the F distribution is two numbers. So one is the degree of freedom for the chi-square in the numerator. The other one is the degree of freedom for chi-square in the denominator. So we say that F is distributed with F distribution and with K1 degree of freedom and K2 degree of, so the K1 is the degree of freedom of the numerator, K2 is the degree of freedom for the denominator. And as you can see, because F is a combination of two chi-square distribution, remember chi-square was always positive. So what do you expect to see for F? Always positive. What do you expect to see for the shape? It's going to be very close to chi-square, but the degrees of freedom are different. So again, I want you to remember F and chi-square are always non-negative. So they are non-negative, positive. We use non-negative because we want to include zero as well. But positive does not include zero. So again, if you see me using non-negative and positive interchangeably, for this type of thing, it really doesn't matter because zero is not going to play an important role there. All right, but and it always look like this. Okay, so these are the things that I want you to remember. And what else we have? So we say F has F distribution with K1, K2 degrees of freedom. K1 is called the numerator degree of freedom, and K2 is called the denominator degree of freedom. So why are we doing this? Why are we reviewing the proper, at least mathematical formulas for normal T, chi-square, and F distribution? The short answer is that if you want to memorize the stuff, honestly, it really doesn't matter. When I tell you that, okay, we are hypothesis testing, I'm seeing if one variable is significant and the test score is going to be, has a distribution which is T. Or if I'm doing joint hypothesis testing, the test score has a distribution of chi-square. So you can memorize this stuff. But if you're curious why the joint hypothesis test has chi-square distribution, you should remember that because, for instance, chi-square distribution is a combination of a bunch of those things. And later on in the course, I'll come back to these intuitive slides, these 4 slides, and show you, for instance, why joint hypothesis testing, the t-stat is distributed with chi-square. Because most of the time you read textbook and you memorize the stuff, you don't realize why. When I say you, I mean all of us, right? We don't realize why necessarily, what's behind the scene, why we say that, okay, that thing is normally distributed, that thing is chi-square, that thing is f, and etc. Okay. Now, so we're done with the theory part. Now let's go to the R version. So the functions that we're going to use in this course, or these are really basic functions in statistics. You can read the R textbook online as well, which to give you an example of each of these things. But I will walk you through to the R script today and show you a bunch of them very quickly. So if you want to take the average of x, the function is mean. For the median, the function is median, right? So these are very straightforward. For variance, the function is var. Standard deviation, the function is SD. Covariance between two random variables, correlation between two random variables, COR. And the quantile, we use it, the function is called quantile. Okay. And I'll give you examples of these things when we get to R. All right, and then lastly, so this is the last slide. Let's see how we can calculate, for instance, the area under the curve for normal distribution, and the area under the curve for chi-square distribution using R, right? Because if I want to do it manually, it's going to be difficult, right? And I'm going to show it to you maybe in the next video that what it takes if you want to calculate these things manually. But before that, let me introduce you the notation, and then we'll get to the next video. All right, so what do we have on top? We have PDF or PMF. Okay, guys, I didn't talk about this PMF in the previous video, but it's basically stands for probability mass function. And some textbook use PMF, probability mass function, instead of PDF for discrete random variable. Okay, but for continuous random variable, we always call it PDF. So I prefer to do, regardless of the type of, if it is continuous or discrete random variable, I prefer to call it PDF. But if in some textbook you saw people are using PMF, they mean the PDF or the discrete version. But very rarely people are using PMF. So whenever we say PDF, you know what you're talking about. So we have PDF, CDF, quantile, and random numbers. So each of them are distributions. So for instance, if you're talking about discrete distribution, what type of distributions we have from your stat course? We can have Bernoulli, binomial, hypergeometric, Poisson, and geometric, right? And then when it comes to continuous random variable, we have uniform, logistic, exponential, standard normal distribution, log normal, chi-square, T, and F. Okay, I'm going to highlight the ones that we use for the course. So the one that we are going to constantly working with are normal, standard normal, chi-square, T, and F. That's it. So from this table, I want you to remember, at least learn the highlight at once. Okay, and then how we do these things in R. So let me see if I use blue. Whenever you want to calculate the PDF, so you have to write the name of the distribution, and before that you have to use letter D. You see this D? D stands for density. So we're looking at density of a distribution, right? So this is what we call PDF. So we show the PDF with letter D in R. D plus the distribution. Whatever it is. If it is normal, we call it D norm. If it is T, we call it DT. If it is F, we call it DF. If it is chi-square, we call it d chi-square. Okay. Then the next letter that we're going to explore is P. And so if you wanted to calculate the CDF, the area under the curve of the PDF, we use P. So for instance, if it is normal, we say P norm or P chi-square or PT or PF, right? The next letter is Q. So Q stands for quantile. So we do Q norm, Q chi-square, and etc. Okay. And finally, the last one is R. And by the way, these are some standard notation that we use in R. It's if you ask me why we use P for CDF or why we use Q for quantile, the answer is no. It's subjective. The author of the package decided to go that way, but it's a fair. These are all fair acronyms, right? So I use maybe Q for quantile, R for random numbers. So this is generally accepted. And give you a bunch of examples and then we move on to R. So for instance, if you want to, let's actually look at this example. If you want to calculate the area under the normal distribution and it has the expected value mu and a standard deviation, let's say the variance is sigma square. Okay. If you want to calculate, let's say this area, what is this highlighted? What is this shaded area? This is the CDF. Let's say this is mu. I don't know, mu is 5, and here we are talking about the number 2, and my variance is, let's say, 9. Okay. How can I calculate the area to the left? We know from a statistic this is going to be equal to the CDF of number 2, right? Or it's going to be, we show it with capital F, or it's equal to little f of x is, oops, sorry, capital X is less than or equal to, or this is equal to PDF. They're all the same, of x less than or equal to 2, right? Then if you want to calculate this shaded area, we have to do the integral. So this is the manual. If you want to do it manually, it's difficult. So I have to do the integral between minus infinity to 2, and I need to know what is the functional form of this. What is the PDF? This is Gaussian PDF, and if you check the Wikipedia, there's an ugly formula for that f of x. And then you have to calculate this thing manually. But we never do something like this manually in the class, or in general. No one in the world is calculating these things manually. We have computers to do that for us, right? So instead of this, you're going to use R, and R, so what is the function? So you have to read it like this. What do I need? I need CDF. So what is the acronym? So I have to use P. What is the distribution? Normal. So it is P norm. Then, so where are we here? Is it normal or standard normal? It's going to be normal. Oh, by the way, I didn't highlight it, this one. So there's a little standard normal. So where are we? We are here. Oh, sorry, that's D norm. We are P norm. We are here. P norm. We say P norm and X. What is the X that I'm interested? 2. What is mu? Mu is 5. What is sigma? Look at that. I have the variance, but in R, for some strange reason, I think this is the one that I don't like about what the author of the package did, or this formula did. They use sigma, but people are used to see that X is normally distributed with mu and sigma square. So in the textbook, you see the second argument is going to be sigma square. However, in R, the author decided to put this as sigma. Be very careful, okay? So this means that here I need to use 3, not 9. So this is my sigma. And when sigma square is 9, so what is sigma? It's going to equal to 3. So sigma square is 9. So this is a very common mistake that people do in R. And you don't make that mistake. So actually, if you watch the quizzes for this class, you will see that I have asked you to, and I give you a bunch of multiple choice questions. Make sure you pick the right one. So if I do something like this in R, the answer is going to be this shaded area. it will give me a number. Automatically calculate this integral for us. All right, so let's stop the video here, and in the next one we are going to put everything together in R, and it's going to be a very short and quick video because we covered the hard part, which was the theory. Okay.